Kirkman. All right, ladies and gentlemen, we are on 6.3, part 2. In your student companion, we're still looking about the same pages, 124 to 126-ish. But we are going to focus on examples 3. Hold on, I'm in the wrong one. We're looking at examples 4 and 5. Yeah, 4 and 5. Awesome. Okay, reviewing really quickly, this is our traditional exponent function here, exponential function. A is representing our y-intercept, or our initial value, and b to the x power is our kind of slope, or what our curve is going to look like, how quickly it's going to curve up, or if it'll be a slow curve. The x means that we have this constant rate where I'm multiplying a number over and over again for b. So if I compare that to the growth or even decay equations we learned in our last part, remember that our a is still our initial or our y-intercept, but our b has turned into either 1 plus the growth factor, r, or 1 minus the decay factor, r. And that's kind of how they're all connected there. So let's go ahead and look. Our example 4 is kind of looking at models of decay and looking at how things go down. So here we have the pica. So the number of pica in a region is decreasing. How does the decrease in pica populations for years 1 to 5 compare to the populations for years 6 to 10? And here it gives us information that pica populations are decreasing by 8% each year, and that the initial population is 144 picas. So to solve this problem, which would be a very common problem for a scientist, you might even have seen something similar to this in your science class, where we're looking at a population decreasing over time or even increasing. But we're basically going to take our decay function, the function of exponential decay, and we have our numbers here. We know that our initial population is 144. So that's going to be A. We know that we're decreasing by 8% each year, so we're going to turn that into a decimal, and we're going to subtract 0.08. And then we're going to go ahead and solve the parentheses here. So if I subtract that, I'll get 0.92. So this is my decay, my exponential decay equation function. But now we have to figure out the difference between these intervals. So because they're going from 1 to 5, we're going to have to go ahead and make x 1 and make x 5 to find the minimum and the maximum for this year. So all they did was they went in and they replaced x with 1 into the equation, and that's this equation up here. So they're making x1 right here. So if I do 144 here, let me pull up my calculator here. If I do 144 times 0.92, whoopsie, that was too small. 144 times 0.92. I'm going to get the 132 here, okay, and that's approximated. So that's where that came from. And then I'm going to do the same thing, but with my exponent. So if I do my exponent, 0.92 to the function, or raised to the power of 5, okay, and then I'm going to times that by 144. I'm going to get about 95. Again, they're rounding, but that's where those numbers are coming from. And then what they did with those numbers was they found the difference here. And so this is the difference in years, and this is the the difference in population, and this is the difference in years. And they found a rate. So they said that with a change of 37, a decrease of about 37 pica over 4 years, that will make this rate here. Okay, now they did the same thing here, but between 6 and 10. Plugging this in my calculator, plugging this into the equation and solving for 6 as well as for 10, okay? And they did the same thing here. So here's my decrease between the years 1 through 5, and here's my decrease between the years 6 and 10. So what this means is that the pica population decreases by an average of 9.25 picas per year for the years 1 to 5. For years 6 through 10, the pika population decreases an average of 6 pikas per year. The average rate of change for the pika population decreases as the years increase. So meaning it's not quickly falling in a straight line, right? It's got a nice curve. The rate is changing. It's quickly falling and then changing a little bit slower there. So all we did was find our decay function here, and then use the information given to kind of plug in our numbers and solve. So we actually solved 4 different equations and found the difference in order to figure out the information for this problem. So then they're saying, here we have our pika still. It says, how would the average rate of change over years 1 through 5 and years 6 through 10 be affected if the population increased at a rate of 8%? So I would take a look at our initial growth, our exponential growth function, and see if you can do the same thing, but with 8%, and then compare it to what we did on the other page and see, what would change, what would be different. All right, so now we have another word problem in example 5 where we're going to be looking at growth and decay together. So it says Rich is comparing the cost of maintaining his car with the depreciating value of the car. Depreciating meaning it's going down. So when you own a car over time, the value of it goes away because it becomes old. And people don't want to spend as much money on things that are old. So we want to know when the value of maintaining his car will be the same as the value of his car, because at that point it's probably not worth maintaining your car anymore. You probably would get better money selling it and then buying a new one. So it's probably what Rich is thinking. So here's his little red car. The value starts at $20,000 and it decreases by 15% per year. The maintenance cost is $500 the first year, and then it increases by 28% per year. So it's more expensive over time. So to figure this out, because I want to know when this one and this one equal each other, we're going to write the exponential functions. We're going to write a exponential growth equation for the cost, and we're going to write a exponential decay function for his value. So the value of the car, and they got this 0.85 by, so here, let me go to the next page so we can plug it into an equation here and you can see what he did. So he took, so again, we're using the function, his initial value times 1, either minus or plus r, whichever one we're using, to the power of x. So for his first one, the value of the car is decreasing. So it starts at 20,000. And then we're timesing this 1 minus the 15%. And that's where they're getting the 0.85, because 1 take away the 15% makes the 85%. So 100. Okay. And they're using 20 here instead of 20,000. What they just did was kind of reduced it, divided it by 1,000 to make it more manageable. The problem underneath, you can see that instead of doing 500, so what they did here was they did the 20,000 divided by 1,000 to kind of get rid of those 3 zeros. And what they did was they did the same thing here, but notice that if I take 500 and I divide by 1,000, I don't have the same, I get 5/10. Don't have the same amount of zeros. So instead of just 5, it becomes 5/10. So that's where they got the 5/10. And then again, this time we're adding that 28% to 1. So that's where they're getting right here, the 1.28. So anyways, we wrote 2 exponential functions. And then they graphed them. So they used like a graphing calculator, or you could make tables to graph these problems. But basically this graph here, the red one is the cost of maintenance, and here is the cost of the value of the car, and the solution is where they cross, just like when we were crossing 2 different linear equations, and where they cross was the solution. The same works for 2 different exponential functions as well. So the point here is 9 and 4.5, and what that means is that the value of the car and the cost of maintenance are both about 45,000, because remember we divided by 1,000. So would you multiply this by 1,000? Because this is the cost in thousands, 4.5 thousand, at 9 years. So in 9 years, they're going to be the same cost. And so at that point, you probably want to sell your car if it has lots of problems, and you're constantly doing this lots of maintenance, if you can afford that. Now, to remind you, how am I graphing these lines? I'm going to be graphing them by making tables. So I would have a table here with X and Y values, and I would be using, we'll use the value of the car first. So this would be the 20 and the 0.85X, and then I'm picking those numbers. Now, it wouldn't actually make sense to use negatives here because we're not going to have an X value of negative years, so we can go ahead and just start at 0. So you can go and say 0 years, 1 year, 2 year, right? And you can graph some of those points so you can start to get your curve, or they use a graphing calculator. And then you plug it into the equation, and then they would do a secondary graph for the secondary curve function. But this one would be for the maintenance. Okay, and then same thing, we're not going to start our maintenance here. Isn't going to start at 0 or negative years. We're going to start at 0. And then you would graph that. And then that's how you're going to get your curves if you were graphing by hand, or you could use a calculation. A lot of the times you might even just be given the graph here and you have to try to find the solution, but they work very similar to when the two lines cross. Okay, so your job is to take a look at Rich again. So Rich is comparing the cost of maintaining his car with the depreciating value on the car. When will the cost and the value be the same, which we figured out. But here, okay, explain how to use tables. Oh, it says on a graphing calculator, but we have our tables right here. So ignore this graphing calculator part. Just how do we use these tables? Let's see if you can re-explain that. It's kind of the same thing. We're going to do another problem as well as an example, but take a minute and think about that. So here's another problem that's similar to the last one. So here we have 2 sizes of seaweed plants that are growing in a cove. Due to changing water temperatures, the bigger seaweed plants are thriving while the smaller plants are dying out. There were originally 25 large seaweed plants and 300 small seaweed plants. The large is increasing by 2% a year, and the smaller is decreasing by 6% a year. And we want to know, when will the number of each type of plant be equal? So the first thing I'm going to do is write my equations. So I'm going to go ahead and do that. You do it as well, and then pause the video and then see if right. So over here I wrote my 2 equations. So I have my large here at 25 times 1.02 to the power of x, and my small is 300 times 0.94 to the power of x, and you can see here that those equations are true. Then we would graph our equations, okay? And we want to know when they are the same, and the point of intersection is at approximately 30 years. So we would say that in about 30 years, the seaweeds would be the same. So that's just another example of how those two go together. All right, so we're going to practice some questions of just kind of understanding growth and decay. So go ahead and give a try for essential question number 1. I believe this is on page, let me go back really quick, 126, I think. But we're going to do number 1, 3, and 4. So tell me, what kind of situations can be modeled with exponential growth or exponential decay functions? We're going to skip this one. It talks about simple interest and compound interest, but we did not. It was not required for us to know about compound interest, so I skipped it for simplicity's sake. Go ahead and do the error analysis. LaTanya says the growth factor would be 25%, and what mistake did she make? And then number 4 is, why is the growth factor 1 plus r for an exponential growth function? So this is really understanding this and going back and trying to make sense of this equation. Remember, I did 1 in 2 equations or functions in 1. I did the growth one with the plus and the decay one with minus in this example over here. But go ahead and give those a try, and then we'll talk more about it in class.